Okay, so hi everyone. Yesterday we saw how to build some field extensions and how to deal with Java groups. Today I will speak about algebraic number theory and how to understand the output of number field in VeriGP. So we are looking at a number field K defined by a polynomial which I will call P, and you can also write it as Q of alpha, where alpha is the root of P. So we saw that yesterday. This polynomial has to be irreducible and monic, and you can, if you want, initialize your number field with this function, NF. Just put your polynomial inside. Okay, well, the polynomial of P is F. I'm sorry. So this output contains all the structure of your number field. You can have easy access to something inside. We'll do that later. I told you yesterday that you have some function called head abs, and also called head best that permits you to find a better polynomial to define your field. This colored apps will return you a canonical polynomial, I mean the one used in LMFDB database, but it may be a bit long. This function is faster, but maybe you will not have the canonical polynomial. It will be better, but not maybe the better one. So when you initialize a number field with NF in it, you can after that access easily to the polynomial used by k.pol, the signature of your number field. So here we have two real embedding, one complex embedding. You can also have the number of real and complex embedding with R1 and R2. You can also have the discriminant of your number field with disk, and k.p gives you the list of ramified primes. So this is the divisors of the discriminant. So here my number field is ramified at 5 and 79. K.zk gives you a basis of the integer ring. Oh, I'm sorry, I did put some French. I was tired. So the integer ring of K is this. So here you have the 1. This term can be written like that. Remember, x is the variable of your polynomial. So it's you can see it as alpha, where alpha is the root of your polynomial. So that's why I write everything with alpha. This third term is this one. So you can denote this one by omega, and you have this simple expression. Then elements. How to represent elements on a number field. You have two ways to represent elements of a number field. The first one is to express it with your basis, omega, alpha, omega, alpha. This is the first way. The second way is to define it modulo your defining polynomial. So you can, so this is a polynomial in alpha. This is linear combination of your integral basis. You can switch between one to the other with alpha basis. So you are giving an algebraic representation, for example, x squared, here alpha squared. It will give you its coefficient in the basis, or you give the coefficient on the integral basis, and it will give you the polynomial in alpha. Okay, so you can go from one to the other depending which one you prefer. Here, it's P. It's the polynomial I use to define the number field.
What is the
Because x is a variable, and if you want to see x as the root of the polynomial, you have to look at this polynomial modulo the defining polynomial. Okay? So that alpha is a root. So you can want to do some operation with your number field elements. You can add elements, you can multiply elements, you can get the norm, you can get the trace quite easily. Every function begin by NFL, meaning number field elements, to say I will use number field element. Here for multiplication, norm, trace, you have also add and power, force power. You can use either a representation or another, depending what you have. Always specify the number field first, then your element. And if you want to multiply, you need a second element. And you see that you can use different representation of elements. It's totally okay. Okay, the function NF to basis and NF basis to alpha is included inside. So here, for example, if I want to multiply 1 minus omega by alpha squared, it will give me that. So it's minus 1 plus 3 omega plus 1 alpha minus omega alpha. If I want the norm of x minus 2, it's minus 1. The trace of x omega minus 2 alpha is 2. Then you may want to look at prime decomposition in your number field because it's something we do quite often. You have this function, ideal prime dec. You give the number field, you give your prime, and it will give you some vector with as components as the prime ideal that you have. So here, 5 is the product of 2 prime ideals, 1 and 2. Here, hashtag is for the length of a vector. So you have 2 prime ideals above 5. We can call them P1 and P2. If you want the residual degree, you just put .f. If you want the ramification index, you have .e. Okay, so for P1, you have residual degree 1 and ramification index 2. And if you do the same, and you can also get a generator of this idea. But, I mean, a system of generators. Here you have you need 2 elements to generate this idea. You need 5, and you need minus 1 plus alpha. So this idea has this shape. And we can do the same for the second one. Here you have residual degree 1 and ramification index 2. And you can have also a generator system if you need. So sometimes we have ideals that are not right. Often something like that. But you can also use it. You just have to know that it's represented by a matrix, which gives you a description of your ideal in terms of the element of your integral basis. Here, if we try with my first ideal that I had, P1, you can see that P1 is 5z plus 3 plus omega z plus 4 plus alpha z plus 3 plus omega alpha z. So it has this shape. So let's call A the ideal given by that in the integral basis. The matrix associated to is that. And you can also have norm of any ideal with ideal norm to specify the number field than your ideal. So here it's huge. But as you can see, the norm is just the determinant of this matrix. So you can also do some operation with your ideals using ideal something. So ideal power is to compute the power of an ideal. So here, for example, we are computing P2 to the power of 3. Then you give the number field. P2 was my second prime ideal above 5. And the power of 3, it will give you a matrix, Hermite normal form. And we already know that this is of norm 1. You can check it. No. Okay. No. Okay. So you can compute the power of an ideal. You can also add some ideals. Here I make the addition of A and P2. Remember, A was this ideal here. And if you add P2 to A, you get something of norm 1. So it's that means that A and P2 are coprime because you get this implementation. I'm pretty sure that there is also a function like ideal coprime that just check if your two ideals are coprime or not, and maybe it will give you back another ideal so that you have like A times B plus Q equals 1. So there is something like that. You may notice. So we can factor any ideal into a product of prime ideal with the function ideal factor. You get a 2-column matrix. You have first the list of all the prime ideal, and the second column all the exponents. So here, if I try to factor A, my last A in K, I get a matrix with 3 lines and 2 columns. 2 columns, I already knew that. That's 3 lines. That means that it's the product of power of 3 different prime ideals. So if we look at the first line, if we look at the first line of this matrix, this is related to the first prime ideal. So it's a prime above 2. With residue degree dot f is the residue degree. So it's a prime above 2 with residue degree 2, ramification index 1, and the power is 2. So finally, you know that the first prime that you get is a prime above 2 and ramified with residue degree 2, and that you have to put it to the power of 2. If we look at the second line, and we do the same, the second prime is above 5. It's ramified because you have a ramification index 2, and it's to the power of 2 also. And here, in fact, we can check that this second ideal is the prime that we called P1 earlier. So to check something like that, you will double it for a second. So it's P1 squared. And the last one is a prime above 13 and ramified with residue degree 2, and which appears before 1. Okay, so I didn't write it, but finally, we know that this A can be written as something to the power of 3 times P1 to the square times something. Okay. Another thing, you can use the Chinese remainder theorem with ideal Chinese. So here, we are looking for an element of that K such that P is equal 1 mod P1 to the square, and B is equal to -1 mod P2, just P2. Here we are looking for that. So I call this element B. So this function will give you back B. And after we can check the valuation of B -1 in P1, we should find 2. And the valuation of B +1 with respect to P2 should be 1. And so we really have something. So then you know how to represent primes and ideals, how to deal with, how to factorize everything. You may want to have a look to units and class group of your number field. So if you want to have a class group and units, you need more information than just the structure of NF units. So just use, instead of NF units, use BNF units. Okay. Here you can put either your defining polynomial or an NF structure. If you already have NF unit of something, use it, because it will not compute again everything which is already known. Okay, so I denote it by K2. So K2 is exactly the same than K plus other things. So you can recover K, so the NF structure, by putting .NF. After that, you can have a look to the class number of your number field, which is here 1. So this number field has a trivial class group. You can also have access to the torsion unit. And so either you use TU, like torsion unit, or if you just want that term, you can use NF root of 1 of K, I mean root of 1. So here, K has 2 roots of unity that are plus and -1, of course. And you can recover it with NF root of 1. You can also get a system of fundamental units by .fu, like fundamental units. So here, again, you get some polynomials that you may understand as polynomial in alpha, if your number field is Q of alpha. So here, the 3 parts of the invertible of the unit, the 3 parts of that is generated by half of alpha squared minus half of alpha minus 1/2, this. And here we have half of x alpha to the power 3 minus 3/2 of alpha squared plus 3/2 of x minus 1, that can be written like that. So these are a system of fundamental units. So let's change our number field, because we have trivial class group. We want to have a class group just for the example. So here, let's consider this one. So I change my polynomial and I initialize it with BNF units because I want to have access to that group. And that psych gives you the structure of your class group by product of cyclic groups. So here it's Z/2Z times Z/2Z. And you can have some generators. Gen. So here you have 2 generators. The first one I call it G1, which is that, and the second one G2, which is this one. Here it should be a 2. Okay, so these are matrices in the HNF form that we saw earlier. Okay, so these are not vectors. Here and there, you can see semicolons. So now, matrices. You can want to know if your ideal is principal or not. So for that, you have this function, DNF is principal, that will give you the class of the ideal in terms of the generator of your class group. So here, let's take the prime decomposition of 13, and I take the first ideal appearing in this prime decomposition. When I try benefit principle, you have to mention your membership and the ideal. It will output two things. The first one, let's G after. The first one is the list of the exponents with your system of generators. So here it's G1 to the 1 times G2 to the 0. And the second term here is an ideal that you may have to multiply with. So here my ideal is not principal, but its square will be, because we have the two torsion elements. Here it's 2 power 1, and remember we are in Z over 2Z. So if you compute the square of that, you have something principal. And if I ask for G, remember the idea of the beginning, I get that. And if I look at the HNF matrix of my time ideal, I can see that this is exactly the same thing than multiply J, so this one, with ideal factor back of this. Ideal factor back is the not the converse. I mean, you have factor and factor back. So here you have your number field, a list of generators, and then a list of exponents, and it will just put it everything together. So here we have this form. Factor back will give you that. Okay, you give G1, G2, and then the vector 1, 0. So it will give you that, and multiply by J. So this is what I tried to write here. So now we know that our prime is two torsion elements. We can compute the generator of its square. So I use ideal form to compute the square of P. And then benefit principle. Give me these two things. The first one is the list of exponents. I see 0, 0. That means that my ideal is principal. And G2 will be will be a generator of my ideal here in the form that we saw at the very beginning of the session. And then you can ask for the matrix, HNF matrix. So you get a generator of P2. And you can use everything that I mentioned to find solution of norm equation. You use for that BNF is int norm. You specify the number field and the norm that you want. Here, there is no ideal of norm 5 in L. Okay? If it can find an ideal, it will give you the ideal as a polynomial in alpha. And then if you want the coefficient into the basis, you just use I to basis. So here, if I'm one idea of norm 65, which is alpha square plus 4 alpha minus 30. No, and yeah, we have three, you know, this one, and this one. So we can see that minus alpha plus 2 is of norm 65. Yeah. You can also ask if you want to, because these are of norm 65 up to multiplication by elements of this positive norm. You have several flags that allow you to give more precision of about the kind of idea you want to have at the end. So just have a look to the documentation if you want to know more. And the last thing that I want to speak about is units. It's about units. So believe me, this one is a unit. If you don't believe me, just check. You compute its norm, it's one. So it's a unit. We found the unit. By using BNF's units in L with this unit U, you will have something that permits you to express your unit in terms of the generators of the unit group. So here you have the list of exponents. So you have your first generator to the 1, the second to the 2, and the last to the exponent 0. So if we list our fundamental units, we have that. So we know that finally U is this first element to the power 1 times this second one to the power 2. And we get that. And the last term here is for the -1, which is your torsion unit, non-trivial torsion unit. So here you can have an expression in terms of your basis. So I will stop here. There are so many things that I wanted to say about algebraic number theory. For example, I wanted to speak about class field theory and relative number field, how to deal with some extension of an extension. It would have been very, very long. So what I decided to do is to put some exercises in the exercise sheet with all the name of all the functions so that you can try by yourself to compute something with, for example, how to compute the Hilbert class field or how to compute the Ray class field or everything. So just have a look at the exercise sheets, and if you have some question, I can answer later, but it was too much for one lecture. So thanks for your attention, and let's try.